Welcome to AI Peer Review, where we really try to cut through the noise on AI research. Today, we're diving into something that's become a real headache for vision language models, VLMs, handling high-resolution images. I mean, these models are amazing for understanding complex charts or like really dense documents where detail matters. But the second you feed them a properly high-res image, they often just slow right down. It's a huge computational bottleneck, especially for real-world uses where speed is, well, everything. So we're looking at a really interesting paper today. FastVLM, Efficient Vision Encoding for Vision Language Models. It's by Pavan Kumar and Asosa Luvasu and colleagues from Apple. And they basically tackle this exact efficiency problem head-on with a pretty novel solution.
Yeah, and our mission today is really to unpack how FastVLM, particularly with its fast VHD vision encoder, manages to get this optimized balance between image resolution, speed, and, of course, accuracy. For you listening, especially if you're technically savvy, we want to get into the weeds a bit. Look at the architecture, the results, find those sort of aha moments in the design that let them scale things up without killing performance.
Okay, so let's unpack that core issue first, high image resolution. Why is it so important for VLMs? You mentioned charts, documents.
Exactly. Think about reading text in an image or understanding fine details in a diagram. You just need that resolution. Low res won't cut it.
Right. But then why do the standard tools like vision transformers, VITs, why do they struggle so much when you crank up the resolution? What's the fundamental problem?
Well, it really comes down to two main things, and they're linked. First, just plain inefficiency at high resolutions. The VITs chop the image into patches. More resolution means way more patches, more tokens. And that directly hits your compute budget hard.
More tokens, more compute. Makes sense.
And second, that explosion in tokens leads straight to increased latency, specifically something called time to first token, or TTFT.
TTFT?
Yeah, that's the total delay. It's the time the vision encoder takes, plus the time the big language model, the LLM, needs to sort of digest all those visual tokens before it can even start generating text. It's called pre-filling.
Ah, so it's a two-part delay, the vision part and the language part getting ready.
Precisely. And for anything interactive, anything real-time, that TTFT is absolutely crucial. If it's too long, the application just isn't practical.
Okay, so it's not just the vision encoding itself, but the sheer volume it dumps onto the LLM. Now, people have tried fixes, right? Things like continuous pre-training or these tiling strategies, Sphinx, Anyrays, S2.
Yeah, there are definitely workarounds out there.
But they often feel like, I don't know, Band-Aids. Do they really solve the underlying latency and pre-filling problem?
Often, not fully. They can help, but they still tend to result in pretty high latency. Especially that LLM prefill time can still be a major issue. They don't always fundamentally change the token count problem.
Right, and this is where this FastVLM paper gets really interesting then. Instead of patching, they went back to basics.
Kind of. They looked at these hybrid architectures, mixing convolutions, the older image processing workhorse, with transformers.
Specifically, they adopted a FastVIT architecture, inspired by Mobile Sleepy's encoder.
Exactly. They picked FastVIT, specifically the MCI2 variant from Mobile CLP.
So what's the secret sauce there? Why is a hybrid model like FastVIT a better starting point for this high-res VLM challenge?
It's really about getting the best of both worlds. First, the convolutional part gives you native resolution scaling. Convolutions are just inherently good at handling different image sizes efficiently. Transformers sometimes need more complex tricks.
Okay, so better handling of different resolutions from the get-go.
And second, and this is huge, token reduction. FastVIT generates way fewer visual tokens than a standard VIT. The paper mentions like 5.2 times fewer tokens than a VIT with a patch size of 14.
Wow, 5 times fewer tokens.
Yeah, and that directly slashes that LLM pre-filling time we talked about, which is a massive win for the overall TTFT, the total latency.
Okay, that makes a lot of sense. Fewer tokens for the LLM to chew on.
And the performance holds up, or even gets better. If you look at Table 1 in the paper, they show something really cool. When they scale FastVIT up to a 768 by 768 input, it produces about the same number of visual tokens as a big VITL14 does at only 336 by 336.
Same token count, but higher input res for FastVIT.
Exactly. And yet the FastVIT setup gets better results, especially on those text-heavy benchmarks like TextVQA and DocVQA, and it encodes the image much faster too. Better quality, faster speed, similar token budget.
That's a really compelling trade-off right there. The paper also mentions using multi-scale features from FastVIT, so taking information from different processing stages. Does that help?
It does seem to. The idea is that features from earlier stages capture finer details, while later stages get the broader context. Combining them should give a richer representation.
And did it work out in practice?
Yep. Table 2 shows their experiments. They found that using depthwise convolutions, a sort of efficient convolution, to pool these features together gave a slight but measurable performance bump for FastVIT. It just shows how these, relatively small architectural tweaks in how you combine information can actually yield real gains. Smart design.
So FastVT was already looking pretty good, but they didn't stop there, right? They introduced FastVT a new encoder.
That's right. FastVT the HD likely standing for high dimension or high definition, maybe both, is their novel design, specifically engineered for high-res VLM efficiency. This is really the core innovation.
Okay, so what did they change? How did they push it beyond FastVT?
Well, they first realized that just making the self-attention layers bigger or deeper in FastVT, which some previous work did, wasn't the best way. In fact, figure 3 in the paper shows that approach could actually end up slower than a well-tuned pure convolutional network like ConMXDL. So naive scaling was suboptimal.
Interesting. So just throwing more parameters at the attention layers wasn't the answer.
Exactly. The key innovation, the really clever bit in FastVT is adding an extra downsampling stage early on. If you look at figure 2, the architecture diagram, this extra stage means the heavy self-attention calculations happen on feature maps that are downsampled by a factor of 32.
32? Wow, that's quite aggressive. Compared to what?
Compared to, say, a factor of 16, which is more common in models like Vitamin they compare against.
And the impact of that extra downsampling?
Massive. First, it significantly cuts down the image encoding latency itself. Second, it results in generating 4 times fewer tokens for the LLM compared to the original FastVIT.
4 times fewer than FastVIT, which was already much better than VIT.
Right. And compared to that standard VIT L14 benchmark at 336 resolution, FastVT produces an incredible 16 times fewer tokens.
16 times. Okay, that explains a lot about the efficiency gains.
Definitely. Architecturally, it has 5 stages. The first 3 use these rep mixer blocks, think efficient convolutional mixers for local features. Then the last 2 use standard multi-head self-attention for global context. It's sophisticated, but still parameter efficient. Around 125 million parameters. That's smaller than many popular VITs, even though it's more complex than the original FastVITs.
So smart architecture, fewer tokens. How did this new FastVT perform right out of the gate on standard tests?
Pretty impressively. Table 3 shows it gets competitive results on CLIP benchmarks.
Yeah.
Compared to VPL14, it's about 2.4 times smaller and almost 7 times faster.
7 times faster. That's huge.
Yeah. And it also beats Vitamin in retrieval tasks, being smaller and over 5 times faster. And Table 4 shows it outperforms a strong convolutional model, Convexy XXL2. It's nearly 7 times smaller and over 3 times faster for VLM stuff. It really seems well optimized. Now, beyond just the encoder, the paper does a great job looking at the whole system. That interplay between the vision encoder and the language decoder, they systematically study this accuracy-latency trade-off considering everything. Input resolution, token count, token quality, LLM size, encoder speed, LLM prefill time, all of it.
Right, because it's not just about making one part faster. The whole pipeline has to work efficiently together. They use that Pareto optimal curve idea in Figure 4 to visualize this, which I always find helpful. Can you remind us what that shows and what it revealed for FastVT versus FastVFET?
Sure. A Pareto curve basically shows you the best possible performance you can get on one metric, like accuracy, for a given level of another metric, like runtime or latency.
Yeah.
You can't improve one without hurting the other along that curve. And Figure 4 makes 2 things crystal clear. First, FastVT's curve is just way better than FastVT's. It sits significantly higher and to the left.
Meaning,
for the same runtime budget, FastVT delivers over 2.5 points higher accuracy on their average metric. Or, put another way, it can reach a target accuracy level up to 3 times faster than FastVT. It's just a fundamentally better trade-off.
3 times faster for the same accuracy.
Wow. Okay, what was the second finding?
This one's really interesting, maybe even counterintuitive. It's the LLM resolution pairing insight. Their results strongly suggest that pairing high-resolution input with a small LLM is actually suboptimal.
Wait, really? You'd think more detail is always better. Why is feeding high-res to a small LLM bad? Because, as Figure 5 illustrates, the small LLM just can't effectively use all those high-detail visual tokens. It gets overwhelmed. In that scenario, the overall time to first token, the TTFT, gets dominated by the vision encoder's latency, not the LLM processing. You're
Yeah.
spending compute creating all this detail the LLM can't really leverage.
So you hit diminishing returns. The encoder works hard, generates loads of tokens, but the small LLM can't keep up, and the whole thing slows down anyway.
Exactly. It's a crucial insight for system design. You need to match the LLM's capacity to the visual information you're feeding it. It's not always about maxing out resolution.
That definitely challenges the more data is always better mantra.
Yeah.
Very practical advice. Okay, so related to resolution, how should we scale it? The paper compares directly changing the input resolution versus using tiling methods, like AnyRays. What worked best for FastVTHD?
Looking at Figure 6, the conclusion is pretty clear. For FastVTHD, directly setting the model's input resolution generally gives the best accuracy-latency trade-off. Tiling, or dynamic resolution, only really showed a benefit at extreme resolutions, like 1536 by 1536, and even then it seemed linked more to memory bandwidth limits than an inherent advantage of tiling.
So the model's internal scaling is efficient enough that just feeding it the target resolution directly usually works best?
It seems so. And if you do have to tile for memory reasons, using fewer larger tiles is better than many small ones. It suggests the built-in hierarchical scaling is doing its job very well.
Okay, another comparison point. Token pruning. Lots of models encode everything and then try to throw away unimportant tokens. How does FastVTHD compare since it aims for fewer tokens from the start?
That's another area where its design really pays off. Table 5 shows that FastVTHD, just by its nature, reduces tokens more effectively than popular post-hoc pruning methods applied to models like VUT. Even at a low input resolution, like 256 by 256, FastVTHD can get down to just 16 visual tokens and still outperform many pruning techniques.
So it simplifies things too. No need for an extra pruning module.
Exactly. It builds efficiency in rather than adding complexity later to achieve it. It's a cleaner approach.
All right, this all leads to the big question. How does it stack up against the state-of-the-art in real-world tests? The paper uses an M1 MacBook Pro for benchmarking, which feels very grounded.
Yeah, the on-device benchmarking is great. Table 6 has the main comparison results, and they're pretty strong. First, against other hierarchical backbones like Convolava, FastVLM, using FastVTHD, significantly outperforms it on text-rich tasks. We're talking plus 8.4% on TextVQA, plus 12.5% on DocVQA, while being 22% faster. And the gap gets wider at higher resolutions.
Beating Convolava quite handily then. What about models trained on huge datasets like MM1?
Good question. FastVLM matches or beats MM1 across benchmarks, which is impressive given it generates 5 times fewer visual tokens. And with more instruction tuning data, their later FastVLM versions actually outperform MM1 and another strong model, LLVNXT, specifically on those resolution-sensitive text tasks.
Okay, very competitive there. Now, what about models that cheat a bit by using multiple vision encoders?
Ah, yes. They compare it against Cambrian-1, which uses that multi-encoder approach. FastVLM, using just its single FastVHD encoder, outperforms Cambrian-1 while being, get this, 7.9 times faster.
Nearly 8 times faster.
Yeah, because for Cambrian-1, those multiple encoders just dominate the latency, the TTFT. FastVLM achieves better or similar performance with way fewer tokens and drastically less compute.
That really highlights the efficiency win. One smart encoder beats multiple less efficient ones.
It really does. And finally, they show the impact of the LLM choice. Swapping from Vicuna 7B to newer Qwen 2 LLMs boosts performance significantly. But maybe the most striking result is a small FastVLM using a tiny Qwen 2.5B LLM. It still outperforms the Lavia 1 Vision, which uses the same LLM, but FastVLM is 85 times faster.
85 times faster, just by having that efficient FastVTHD front end?
Seems like it. Even though the FastVHD encoder itself is smaller than the SIGLIP encoder used in Lavia 1 Vision, it just shows how crucial that efficient vision processing is for the whole system's speed.
So bottom line, FastVLM seems to consistently deliver really competitive, sometimes superior results, while just crushing competitors on speed and efficiency, especially for high-res tasks.
That's the key takeaway, I think. It's a very strong showing for efficient design.
So wrapping this up, what does this FastVLM paper really mean for, for us, for the technically minded listeners, and just for where VLMs are headed?
Well, I think it clearly shows that efficient high-resolution vision encoding isn't just wishful thinking anymore. It's achievable.
It's here.
Yeah, FastVLM and FastVHD feel like a really significant step. They've demonstrated a state-of-the-art balance between resolution, latency, and accuracy, backed by solid on-device benchmarks. It really underscores that smart architectural design, really thinking about that interplay between the vision and language parts, can yield huge gains. You don't always need brute force.
Yeah, this deep dive definitely shows we don't always need bigger models or more complex add-ons. Sometimes it really is about smarter integrated design from the start, rethinking the fundamentals.
Absolutely. And maybe a final thought for you, the listener, to chew on. Given how well FastVi THD's direct resolution scaling works compared to tiling, and that crucial insight about matching LLM capacity, where else in AI, maybe especially in multimodal systems, are we relying on these sort of indirect processing steps or complex workarounds? Where could rethinking the core architecture, aiming for more direct optimized solutions like FastVi THD, lead to similar breakthroughs in performance and efficiency? Something to consider.